As the name suggests, we are going to talk about densest subgraph problem. So now how many of you are familiar with this densest subgraph problem definition? You are not. Okay, then let me just define it for you. So we are given a graph G and if you just look at any subset of nodes V, yes,
you're crossing this side, so we are not able to, all these things are covered in the camera.
oh, this side, this thing?
Yeah. No. If you can restrict yourself till here, it will be fine for us.
No, but I need my nodes, right? I need to keep these things somewhere because in case I need to access this. Okay, let me just keep them here. Is it fine? Okay, sure. Okay, so for any given a subset of nodes V prime, just define the following notations. This is basically just the set of edges in the graph with both endpoints in E prime. Sorry. Now, if you look at any node V in V prime, this is just the set of neighbors of V. In V prime. And finally, this is the degree of the node V in V prime. Now, the density of this subset of nodes is simply the number of edges in this induced subgraph divided by the total number of nodes. And this is closely related to the average degree. What is the average degree? By definition, it's just you sum over the degrees of all the nodes in V prime divided by V prime. Can you tell me how these two quantities are related? Yes. So the average degree is equal to 2 times rho s, rho V star. Then what is the densest subgraph problem? Find a subset of nodes such that this density is maximized. Clear? Now, we will solve this problem in the streaming setting. That is our goal. But first, we want to study this in the static setting. What is known? You can solve this problem exactly in polynomial time by reducing it to max flow problem, but there the runtime is quite high. There is actually a very simple greedy algorithm that runs in near linear time and gives you 2 approximation for this problem. So first we will go through that algorithm. But before that, we will need one particular result, small lemma, that gives some intuition into this problem. The lemma is as follows. So, let V star be the set that maximizes the density. Okay, and let D star be this optimum density, maximum density. The claim is if you look at any node in this set V star, then its degree is at least this star. Now, before getting into the proof of this theorem, let us try to have some intuition. Any idea as to how should we proceed with the proof? It says if you just look at the densest subgraph, every node has degree in that subgraph greater than D star.
So this means D star is half of the average degree.
Yes.
So if it's less than the average, then you.
Yes, exactly. So the idea is if there is a bad node whose degree is less than D star, then you can remove that node and increase the density of the remaining set. Okay? Let us just go through this proof. So you just fix any bad node, say, or say any node, okay, and let consider this set V prime okay. Now what do we know? We know that the average degree in V star, this is exactly equal to 2D. What does this imply? This implies that if you sum over the degrees of the nodes here, so degree u comma V star, what is this going to be? This is going to be 2D star. This is actually, this is going to be 2D star times size of V star. This means so now you look at every other node u and look at its degree in this remaining set V prime. So you are undercounting this quantity, and so you need to adjust. By how much should you add? It should be 2 times the degree of V comma V star, right? Because you left out the node V from this sum, so that's why you get one quantity degree of V comma V star. And then for every other node u, here you are counting the degree in V star, here you are counting the degree in V prime. So overall you are losing again this much amount, and this thing is going to be 2D star times V star. So this is equation 1, and we also know that the average degree of V prime by definition is going to be less than or equal to 2D star, because D star is the optimum density. What does this mean? It means u comma V prime, this is going to be less than or equal to this is 2. Now you subtract 2 from 1. This quantity and this quantity will cancel out, and you will get 2 times degree, this is greater than or equal to 2d star times this quantity is equal to 1. Okay. Now, using this lemma, we can get, okay, so let me keep this thing here. So, using this lemma, we can get a 2 approximation in linear time. Where m is the number of edges. Okay, any idea how will that go? What is the obvious greedy algorithm that comes to your mind? You start with this entire graph, and okay, if the optimum densest subgraph is the entire graph, you are done. Otherwise, you have to remove some node, right, to get to that densest subgraph. Which node should you remove? Minimum degree node. Okay. Then you get a remaining graph. Again, if that is the densest one, you are done. Otherwise, you need to remove one node. Which one will you remove? The node with minimum degree. Just do this, perform this algorithm, and I am going to show that this is going to give you a 2 approximation. Okay. So the algorithm is initially V0 is equal to V, and then for I equal to 1 to n.
So the converse of the lemma is also true?
Sorry?
The converse of the
No, the converse of the lemma is not true.
So how are we checking whether it's the densest graph?
Yes, the idea is you will get n different subgraphs here, right? Just pick the one that gives you maximum density. So the lemma is this, that for I equal to 1 to n, let Vi be the node with minimum degree in Vi minus 1. Then you just set Vi to be Vi minus 1 minus Vi. Finally, return the node with the node set with maximum density. Now, first, can you see that this can be implemented in linear time? How are you going to implement this? At each step, you are just taking, so you just maintain a counter at each node that stores the current degree, and then you just extract, okay, in m log n time probably, you just extract the minimum of this counter, I mean the minimum degree node, and you just adjust the degrees of its adjacent nodes. So basically you are probing each edge at exactly once when it is being taken out of the graph. So the overall update time will still be O of m. And now the claim is this algorithm returns a true approximation to the densest subgraph problem. Proof. How will the proof look like? So let D star be the optimum density. Now just look at this sequence of subsets. Okay. So you have V0, then you have V1. This is the output of the algorithm. Let us say Vi. You have Vn, and Vn actually will be empty set. Sorry?
VA is a subset of VA image.
Oh, sorry. What I am saying. No, this is okay. Yes, okay, this is okay. Now, any idea, any guess as to the proof? I just give you the hint. Consider D star and just look at this sequence. What do you need to show? That there is at least one node set in this sequence where the density is at least D star over half, right? I'll just pause for 1 minute, because if you could figure it out yourself, it's even better.
So you look at the number of edges removed in each of the things.
Mm-hmm.
So assume all the vertices you remove have degree less than D star by 2.
Mm-hmm.
And now look at, so when I remove a vertex, the number of edges I delete from Vi to Vi plus 1
Mm-hmm.
is at most D star, is strictly less than D star by 2.
Mm-hmm.
So summing over all of them, it's n in the, I mean, like the total number of edges is less than n into D star by 2. But I know that D star is E by E.
Okay.
D
You
star
are.
is at least E by n.
It's almost exactly the same thing that you were pointing out. I'll just correct one or two minor small bugs. One is that you don't look at D star over 2, you just look at D star as being the threshold. Okay. Now I'm going to rephrase it slightly differently, but you can see that what you were saying is basically exactly the same as to what I am going to say. This end graph is empty. This is the entire graph. Just look at the node that was removed here. What was the node that was removed here? This was V0, this was V1, this was Vi, and so on. What was the degree of V0 at this stage? In general, it would be less than D star, right? Because there are two cases. Case 1, let me just continue the proof here. Case 1. Degree of V0 in V0, this is greater than or equal to D star. Then I claim that V0 itself is a 2 approximation. Why? Because V0 is small v0 is the minimum degree node here. So every node in V0 has degree d star. That means the average degree in V0 is also d star, right? And what does this mean? It means the density of V0 is greater than d star over 2. Now you continue like this. Suppose it did not happen, that degree of V0 here was less than d star. Then you look at V1. Just apply the same argument here. Okay? And you can argue that since d star is the optimum density, there will be some Vi where you will see this thing happening. So the claim is that there exists some I from 0 to n such that degree of Vi how can you prove that? It follows from this lemma 1, because d star is the optimum density. Let V star be the densest subgraph. So every node in that densest subgraph has degree at least d star. So initially, suppose in case 1 you did not found this. So you found that degree of V0 here was less than d star and you removed V0. Then you can see that this entire densest subgraph is actually surviving this step. Right? Because you are never going to remove any node from this densest subgraph until you reach this threshold d star. Okay, let us define these quantities d0, d1 till di and so on. What is di? It's the degree of Vi in capital Vi. Okay. The claim is if d0 is less than d star, then every node in V star survives in V1, right? And then again if d1 is less than d star, then every node from that densest subgraph survives to in V2, and you go on like this, but in the end you end up with an empty set. So a time must come, say in I, where you observe that di is greater than or equal to d star. Then you just apply this argument. Okay? Clear? And you can see this is the most obvious greedy algorithm that will come to your mind when you just think about this problem. Okay. Oh. Let us stay here just for the time being.
How is the exact algorithm? That's some easy enough algorithm.
Yes, it's easy enough. What you need to do is you need to convert this graph into a directed graph. There's a reduction in a specific way, and then you show that if you perform a max flow computation in that directed graph, from that solution you can retrieve the densest subgraph. It's not difficult, but it's unnecessary for our purpose. Okay. Now what is our objective? Our objective is to solve the densest subgraph problem in the streaming setting. And for the rest of this class, we will be just concerned about returning the value of the maximum density, not returning the densest subgraph itself. Okay. Let us look at this algorithm, and can you implement this in a streaming setting? I will just give you a hint, forget about random sampling or anything else. Okay. We just want a deterministic streaming algorithm. So, and also let me tell you, say it is just insert only stream and you are allowed multiple passes. How many passes will you need to implement this algorithm? Trivially. Which one should I erase? Can you see that you will need actually n passes, because in order to figure out the degree, so suppose I tell you that you need to figure out the degree of this guy v prime, that you need to figure out this quantity. How many passes will you need to figure out this quantity? One pass, right? And actually what you can say is that in one pass we can figure out so you fix this subset v prime and you ask me what is the degree of each node in v prime. In just one pass I can return you this quantity, right? You just scan through the edges one after another, keep a counter at each node with respect to its degree, just update this counter and you are just storing n set of quantities. Okay. The problem is that to implement this step we need to maintain the degree, we need to know the degree of each vi in capital Vi. So just for implementing one iteration of this algorithm we will need one pass, and this algorithm runs for n iterations, so we will need n passes. Okay. We need to somehow modify this algorithm so that we can do better. For the time being we will just focus our attention into getting a log n pass algorithm with roughly the same approximation ratio. Yes, not extra space, you are allowed n polylog n space. So basically you cannot store all the edges, you can only store something at the nodes. Okay. So now for the time being we will consider giving a log n pass algorithm. Before that, let us consider this. You just fix some number d from half to n minus 1 over 2. What is so special about this half and n minus 1 over 2? Half is the minimum possible density, because if you just take one edge it gives you a density of half, and n minus 1 over 2 is the maximum possible density. When you have a complete graph your density is n minus 1 over 2. So the density will lie between somewhere here, and suppose you are given some parameter d, you are probably just told the value of the density, and now let us do this. I just want to ensure that I am done with the notation. Okay. So start with V0 being equal to V, and then for I equal to 1 to L, where L is something we will define later on, you just do the same thing. So Vi, no, yes, okay. Just wait. Z0 is equal to V, and Zi is the set of nodes in Zi minus 1 such that clear? So basically the only difference between the previous algorithm and this one is that in the previous algorithm you were peeling out the minimum degree node. Zi was just a single node. You have this graph Zi minus 1, just pick the node with minimum degree. Here we are peeling out a bunch of nodes. Okay? So what are the nodes that are being peeled out? The nodes that are being peeled out are this set. Okay? And what is the idea? The idea is that suppose D is the correct guess, and then at this stage you see that the nodes in this set have degree less than D. Of course they cannot belong to the densest subgraph by lemma 1. You can just peel all of them together. And why this is going to help us? Because this is supposed to reduce the number of passes. Because now in this pass we are actually taking care of multiple nodes instead of a single node. Got the intuition?
So if you had the correct value of D, then would you get into approximation straight away?
Yes, exactly. That was my next lemma. Now the claim is, I am just going to write a variant of what you just claimed. Okay? Consider two cases. Case 1, okay, then at the topmost layer you will get something non-empty. On the other hand,
degree of ZL is not D star.
sorry?
And the average degree of ZL will not be.
Yes, the average degree of ZL will be at least D over 2.
At least, and less than D star.
Yes, it will be less than D star, but it will be at least D over 2. Okay? And the other claim is, for the time being, suppose L equal to N. Okay? Else if D star over 2 is strictly less than D, can you see why this is going to happen? Say this is part A, this is part B. Proof of A. This is not difficult, right? D star is greater than D, and at each iteration Zi is the set of nodes with degree at least D. So the set of nodes in the densest subgraph will belong to Zi for every I, right? So the claim is, if V star is the one that gives you maximum density, then V star is a subset of Zi for all I.
Suppose D star equal to D plus 1, I mean like, then both the first and second thing can be, I mean like the first and second conditions are not exclusive. They can intersect, but the claims can't intersect. I mean, it's probably.
Oh, sorry. What were I saying? It was D over 2. I mean, it's a stupid, silly mistake. Yes. Okay, sorry for the confusion. But let's just look at part A. Is the proof clear? That V star is the set with maximum density. Then just look at any iteration. You are just looking at the nodes with degree greater than D. So all of V star will go into Zi, right? And so ZL will definitely contain V star and it will not be empty. Part A is easy. Part B. For part B, we will claim that Zi is a strict subset of Zi plus I minus 1 for all I. Meaning at each iteration you are removing at least one node. Okay? How can you prove that? Consider iteration I. Let me ask you, can you give me an upper bound on the average degree in Zi, whatever this Zi might be? Average degree of Zi is definitely going to be less than or equal to the average degree of the optimum set, right? By definition. What is the average degree of this optimum set? It's 2 times its density. What we have said, 2 times its density is less than D. So the average degree of Zi is strictly less than D. That means there has to exist some node in Zi yes, with degree strictly less than D. Yes, let's just consider Zi minus 1, sorry. And then this node V will not be part of Zi. So in each iteration you are removing at least one node. After L iterations you will remove all the nodes. Okay. Now note that we are not there yet. Intuitively it's better because in each iteration we are removing multiple nodes. But still in the worst case we might end up with n iterations. Okay. How can we ensure that these two conditions will hold, but we can stop after log n iterations? Just carefully look at the part B, okay, proof of part B, and we want to argue. Earlier what did we argue? Sorry, I should not have erased that. Earlier we argued that, yes, part B, the argument was that the average degree in Zi minus 1 is strictly less than 2D star, which is strictly less than D, and that meant there exists a node V that is in Zi minus 1 but not in Zi. What will be your idea as to extend this argument to say that we can remove possibly a constant fraction of the nodes from Zi minus 1, then we will be done. one. Let me write it here. This is roughly equal to log n over epsilon the algorithm remains exactly the same, okay? We have just reduced L to be log n. And now the claim is this implies B So we have just modified part B by saying else if d star is less than d over 2 into 1 plus epsilon. Everything else is the same. Proof. Part A is exactly the same. Part B. How will you prove part B? Look at this argument again. It's just need to think of one idea.
So d star is some multiple of 1 by n that we can use some so delta of zi minus 1 we know is equal to d star. But d star is some x by n.
Okay.
But d is a integer.
Okay.
So that gap we can probably use. I mean, there's a gap of 1 by n there.
Actually, there is, you are on the right track, but it's even simpler than that. The gap is by a factor of 1 over epsilon, right? So we want to prove part B. Do you agree with this step? That delta of zi minus 1 is less than or equal to 2d star as before, and 2d star is now less than d over 1 plus epsilon, right? Now, what is the total degree? in Zi. It is this quantity, right? Now this quantity is clearly greater than or equal to the total degree in Zi minus 1. Yes, because Zi is a subset of Zi minus 1. And the total degree in Zi minus 1 is this. Oh, sorry, it is the other way around. What am I saying? Z total degree in Zi minus 1 is greater than or equal to the total degree in Zi. Let me write it like this, then it will be easier to see. Zi minus 1 times delta Zi minus 1 greater than or equal to Zi times delta Zi. Okay? Now what is this quantity? We have an upper bound on delta Zi minus 1. What is this upper bound? Okay, wait. Sorry? Oh, the inequality is straight. Sorry, I am actually making it unnecessarily complicated. All I wanted to say was, look, delta of Zi minus 1 is this. Before delving into the calculation, here is Zi minus 1, and we know that the average degree in Zi minus 1 is small. It's d over 1 plus epsilon. And here is Zi. We know that the average degree in Zi is large, it's greater than d. Okay? So then the size of Zi has to be small. Because if the size of Zi is very close to Zi minus 1, the average degree in Zi minus 1 will increase, right? So you just look at this picture that Zi is a subset of Zi minus 1 and say that, okay, this is greater than d and delta Zi minus 1 is small. Oh, sorry. This is what the confusion was. Yes. Yes, sorry. This is where my confusion was. This is large. Oh, yes. Okay.
What is Zi by definition?
Sorry.
All the nodes in Zi have degree greater than.
Yes, with respect to Zi minus 1. Okay. So the claim is this. I mean, this is actually quite simple. I mean, it's my mistake that I made it complicated. The claim is that the size of Zi ought to be less than or equal to the size of Zi minus 1 divided by 1 plus epsilon. Why? Proof. Suppose it's not true. Then what will imply? Then just look at the total degree in Zi minus 1. This thing is going to be greater than or equal to the sum of the nodes in Zi. Okay. Now each of this quantity is at least D by definition. And if Zi is greater than Zi minus 1 over epsilon, you are going to have just now look at this inequality. Divide Zi minus 1 in both the sides, from both sides. What do you get? Okay. What does this mean? The density of Zi minus 1 is and this is greater than D star. A contradiction. Okay. This is something simple. I mean, it's not quite complicated. The main idea is this, that Zi is a subset of Zi minus 1 and the degree in Zi is large enough, whereas the average degree in Zi minus 1 is small enough. So that means that the size of Zi cannot be too large compared to Zi minus 1. And then if this claim is true, then can you see that this lemma is also valid? I mean, let me just make it into a lemma.
The contradiction was that the I minus 1 was not the densest subgraph.
Yes.
So which we did not know.
Yes.
That's kind of.
Yes.
So in the algorithm, I mean, I might get to a densest subgraph and then after that this lemma doesn't hold good.
No.
D star was the densest.
D star is the density of the densest subgraph.
Right.
The contradiction was that.
Oh, it's strict inequality. Fine.
Yes. Okay. So now suppose. So why does the algorithm hold? Because it just shows that in each iteration you are just peeling out at least a constant fraction of the nodes that are left. So after log n iterations you will peel out everything. So this thing follows, right? Now assume this lemma, this algorithm. Can you show me a log n over epsilon pass streaming algorithm for this problem?
what happens when d is between these two values? So if d is greater than this, d is less than d star, so if d is greater than groups like this, what happens in between?
So the thing is, in between any of these two things can happen. You do not know. Okay? So that is the next question.
Can't we like choose? We are the one who are choosing D, right? Can't we like choose D such that?
So here is the thing. Okay, that there comes the next question. Okay, let me just answer this question like this. This is the range, right? This is D min. This is D max. Now suppose you discretize this range in powers of epsilon. Di, and let us say this is dk, where di is basically d0 times, okay. Now actual d star, the opt, will fall between some di and some di plus 1. Look at this dj, where j is dj is
2x. I think j could
d star will have to be, oh sorry, 2d star, sorry. Let us just say this.
2d plus 1 because this need not be, this value need not be a discrete value.
Yes, this value need not be a discretized value, but we, yes, just, okay, you know what I mean. I mean, just look at this d star, look at this quantity, and look at the next dj. Okay, let me even draw this picture even more clearly. Okay, this is di, this is your d star. Now let us say d prime is this. Okay, dj is just this discretized value here. So d prime lies between dj and dj minus 1. Okay, is the picture clear? Now if you run this algorithm for d0 to dk, what will you observe? What will you observe? Here the topmost layer will be empty, and in this range, in this entire range, the topmost layer will be empty, right? On the other hand, in this range, the topmost layer will be non-empty, right? Because you know that d star is less than dj over, okay. In between you do not know anything. So let me give you this algorithm that run this procedure for d0 till dk, find the maximum index I such that ZL becomes empty at DI. Just return DI.
But this won't be RDI, this might be greater than D star, right? Because you say we don't know what happens in D.
Correct.
So this is a 2 into 1 plus epsilon squared.
Yes. Return DI divided by this quantity. Now just look at this quantity. This whole quantity is clearly less than D star by definition. And how much less can it be? The worst ratio will be 2 into 1 plus epsilon square. So you will get 2 times 1 plus epsilon square approximation. Yeah. Yes, 1 plus epsilon cube. So the point is that 1 plus epsilon to the power some constant you don't matter. It will still be 1 plus epsilon if you ignore the lower order terms. The thing is this constant. Okay. So the whole thing is, and how many decays are there? I mean, there are log n many decays. You are just discretizing this thing in powers of epsilon. Okay. So the main idea is that if you can run this procedure in log n pass, then you can run the whole thing in log n pass, right? Because you can run this procedure for different values of di's in parallel. Don't care. Okay. Now the question is, how can you run this thing in log n pass? Just focus on this. I mean, you are given this parameter d. The idea is just simple. Use pass I to determine Zi. So suppose till now you have determined Zi minus 1. Just make one more pass. In that pass, you just figure out this degree of v comma Zi minus 1 for every node in Zi minus 1. You can do that in one pass. And after that, you can just figure out Zi. Okay. Now,
Log squared.
yes, no, log n.
You're doing it in parallel for all values.
You are doing it in parallel for all values of these. So the space requirement will be log square n or something. That's a different thing. But the number of passes is this. Now, we will now see how to make it a one pass algorithm that works in dynamic streams, insert delete streams. Okay. So for that, fix D. We are just going to show that we can implement this procedure in one pass. Then it's fine, right? Because again, we can run for different values of D in parallel. So for the rest of this lecture, just fix D. Now, Recall from our previous lecture, this is where we will be using our previous lecture. In a dynamic stream in one pass, we can actually maintain an L0 sample over a set of universe. So, we can actually maintain some L0 sample corresponding to each node, the edges adjacent to each node. We can also maintain samples corresponding to the entire edge set. That is also an L0 sample, right? I mean, you just consider the entire edge set of the graph. And okay, so the thing is, in one pass, we can maintain an edge E chosen uniformly at random from the entire edge set E using our L0 sampling lemma from previous class. What will be the space requirement? No.
This is polylogarithm.
Exactly. This is just one L0 sample that we are maintaining. What was the L0 sampling lemma? You are just given a vector. In each update, you are just changing one entry of this vector. In this case, what is the vector? The vector is n squared dimensional, one for each possible entry in the edge. And in each update, you are just inserting one edge or deleting one edge. Is it clear, Divya? Because if you do not get this, I mean, so this stands for polylogin. So what is the vector, just so that we are okay with it? The vector is each entry in this vector corresponds to an unordered pair of nodes of this form. So this is just a placeholder for whether this edge is there or not. Now what is this dynamic stream? It either sets this to +1 or 0. Okay, and in each update it just changes one entry from 0 to +1 or vice versa. Now if you maintain an L0 sample here, what will you mean? You will just look at the support of this vector, which is basically the set of non-zero entries, which is basically the set of edges, and from that support you will just pick something uniformly at random. Okay, and you can do that in polylogin space.
So all this is under the guarantee that the updates are like safe. I mean, you can't delete non-existent.
Yes, that is guaranteed. Okay. Now we will use this lemma to run this algorithm in one single pass. What will be the idea? Let me just give you one hint. Just consider about one iteration. How are you going to implement one iteration of this algorithm? The idea is this. Okay. The first assumption is, we can relax this assumption later on. You can just figure it out yourself. It's not difficult to relax. We know the final value of m. And this final value of m is greater than n log square n or something. Why? Because if the final value, okay, you don't even need to, need this assumption. I take it back. We know the final value of n, because note that the value of n changes. This is a dynamic stream, right? At an intermediate step, there might be many edges, then the number of edges can also drop and something else. Suppose we are just given the exact final value of n. Now what are you going to do is, for each I equal to 1 to L, so each I here just corresponds to exactly one iteration of this thing, okay? We are going to maintain Si randomly sampled edges from E, okay? Now what does this mean? First of all, this is not an exact subset. This thing just tells you to maintain this many L0 samplers on this set E. So there might be duplicates in Si. So as if you are picking m log n over d samples uniformly at random with repetition from E. Is this clear what is going on? This is with repetition. And we will use the samples in Si to determine our set Zi. How? We will come to that later on. But first, can you tell me what is the space requirement for this? Because the space requirement is simply the space for maintaining these samples. Everything else you do at the end of the string with these samples. What is the space requirement? Ignoring polylog factors. Exactly, right? Because for maintaining one uniformly random sample, you spend polylog n space. So to maintain m log n over d random samples, you spend m over d times polylog n space. And how many such i's are there? L, which is also log n. So overall, the space required here is, ignoring polylog n factor, this much. Is this too high? Is this too large? We want to have small space, right? We want it to be a semi-streaming algorithm. How large can this quantity be?
But so if m is very large, then d would be correspondingly large.
Sorry?
If m is very large,
Mm-hmm.
I think d would be correspondingly as large, right?
Exactly, that is the idea. Can you give a simple trivial lower bound on d? Exactly. That is just one simple idea. Earlier we were saying that we are going to discretize this range, right? This is our d0, this is the largest value of dk. Okay? But now I just say you can just start from m over n. Let this be your d0. So d has to be greater than m over n. Why? Because if you take the entire graph, you get density m over n. And if that is the case, what is the space requirement? Tilde of n. So we are fine. This is semi-streaming algorithm. Now, Using an SI, we will determine Zi. Which part can I erase? Let me just erase this part again, okay? Can I erase this part? Using SI to determine Zi. How will you do that? So you assume that you have figured out Zi minus 1 somehow correctly with high probability. Now we only have these samples SI.
So the probability that we missed out an edge in Z.
Sorry?
So if we can show that Zi with high probability contains all the edges in SI contains all the edges in Z, then
That would be one way of going about it, but unfortunately that is not going to be true. If it were true, that would lead to a correct proof. I agree. So first note down the parallel. Earlier in the deterministic log-n-sparse streaming algorithm, we were saying, okay, assume by induction hypothesis we have determined Zi minus 1. Now we are going to make a whole pass through the input so as to get these degrees, and from that we will get our Zi. Now we are saying, okay, assume we have Zi minus 1, but we cannot afford to make one more pass.
We can add.
All we are left with is these samples.
We can use this linearity of just add Si and Si minus 1. And if the edges are, if we
perhaps we can say that since the degree of any vertex in Zi has degree at least Zi minus 1 in T. So the probability of no edge in SI being incident on it should be, so we pick m times T over log n thing, right? So we should have at least m over log n.
No, but there might be very few nodes in Zi, right? You do not know how many nodes are there.
So that's why I consider for every node there is some edge incident on it, which is picked in SI.
Okay, and then?
The reason being that that node has very high degree in Zi, and we are picking m by T over log n samples, and it has degree at least T.
Okay, good. That's exactly the idea. That's exactly the idea. Now I am going to formalize it slightly. We have Zi minus 1, right? What is our job? Our job is to distinguish between two types of nodes in this Zi minus 1. This is degree less than D. Let me just introduce some slack and say that I'll just be fine. You can figure out that nothing will change much, okay, if you just introduce this slack. So what I have done? What have I done? Earlier, we were saying, look at the nodes whose degree is exactly greater than D. They belong to one partition. The remaining nodes belong to another partition. Now I am saying, introduce this gap of 1 plus epsilon. The nodes in B, they will definitely go to Zi. The nodes in A, they will definitely be chopped out. And the remaining nodes whose degree are between this, sorry, what am I saying? Sorry for making so many silly mistakes. All I am saying is that it's okay if we guarantee that all the nodes in B whose degree are sufficiently high, they go to Zi. And we guarantee that all the nodes in A whose degree is sufficiently low, they do not go to Zi. And what happens to the remaining nodes? The remaining nodes whose degree are between d over 1 plus epsilon and 1 plus epsilon times d, we don't care whether they go to Zi or Zi plus 1. Okay? So that will be a relaxed version of this algorithm. And you can just figure out the proof that it will just introduce one more 1 plus epsilon squared approximation ratio, I mean factor in the approximation ratio, not difficult. Okay. So now our goal is we have this Zi minus 1, and using the samples Si, we need to distinguish between the set A and the set B. Can we do that? The point is, if you fix any node in Zi minus 1, what is its expected degree? With respect to this sample, expectation is with respect to this sample, okay? What will be its expected degree? Each edge that appears, sorry, this is its actual degree, right? Each edge that appears here, what is the probability that it appears here? Or in other words, you just fix one specific edge E. What is the probability, or how many times in expectation will that edge appear in this sample? I am asking you, fix an edge E, right? What is the expected number of times E appears in SI? Log n by D. Because it appears in one sample with probability 1 over m, and you have taken m log n over d samples. So it's 1 over m times m log n over d. Okay, times and this follows from linearity of expectation, right? There are these many edges. So what do you get? M cancels out. Okay, now let me erase this part. What does this mean? If a node V has sufficiently low degree here, what will be its expected degree in the sample? This is going to be, this quantity is less than d over 1 plus epsilon, right? this is going to be less than log n over 1 plus epsilon. On the other hand, if this guy's degree was sufficiently high, then its expected degree will be large. Okay. Now I am just going to apologize again and say that I should have here said that you pick C m log n over d samples for some constant C instead of m. Okay. C is some constant greater than 0, and you will just see in one moment why. Because then this becomes C log n over d, and this expectation becomes this. And now we can apply Chernoff bound. We can say that if a node V belongs to A, then with high probability its degree in this sample will be less than C log n. If you fix a node V, then the edges adjacent to it, they are being sampled uniformly at random and independently of each other. So you can apply Chernoff bound on this expectation. And recall that in the Chernoff bound, the main deal was that the expectation should be sufficiently large, around C log n, so that you can get high probability bound. And that's why this C log n factor were there in the sample. So for a node V in A, its degree in the sample will be sufficiently small, C log n. On the other hand, for a node in V with high probability, its degree is going to be sufficiently large, greater than C log n. So basically you could identify these sets A and B just by looking at their degrees in the sample. Okay. So identify the nodes in A and B by looking at the degree of each node in SI, then just set Zi to be the guys with the highest degree nodes. This is it. Is it clear? And here you will note that in this class we just used the L0 sampling part, we did not use the linearity of sketch at all. We just wanted to maintain these many random samples. We never added up the sketches and did anything like that, Okay. Yes. Question. Hmm?
So when you wrote degree of t in Zi is related to t. No, so I'm just saying that what we actually do is while sampling, we only maintain samples from the whole graph. Right?
Yes.
So, okay, so this is correct. I was just confused that we don't know Zi minus 1 or anything in the beginning, and yet we are currently mapping.
Exactly.
The reason being that if the degree in Zi is greater equals to t, it also implies that the whole graph is much bigger than t. So
Yes.
that is why.
Yes. Initially, we do not know any zi's or anything. We just maintain this set of samples Si in the streaming part. Then the stream ends, and at the end of the stream, we just take each sample Si to get Zi from Zi minus 1. That is it. And then we see if the topmost layer is empty or not and report accordingly. That's it.